Okay. Yep. Welcome back, everybody. Let's get started. So today we'll have another guest lecture by Kieran Goodall. Kieran is a fourth-year PhD student in my group, so he's like very knowledgeable about E3. You've probably met him in the office hours already, and he'll be teaching you about E3 layouts first, things like force-directed layouts, chord diagrams, pie charts, and so on. If there's time left, I will continue with the last lecture, the visualization alphabet. Okay, Kieran, please take it away.
Hi everyone, I'm Kiran, and today we'll talk about some advanced D3 stuff. Am I audible all the way in the background? And Alex, can you check with Haihan if I'm audible and straight? Okay, great. So till now in the class we looked at the basic D3 syntax of how to take our data, how to bind the data to our D3 elements, and then append it using either the enter, exit, merge, or the join syntax. What we are today looking at is the layouts. So layouts basically are some helper D3 modules that help us map our data to specific new data structures to, for example, calculate things like arcs for our pie chart, or nodes and the links for our tree diagram, or something advanced like a tree map. So D3 layouts, basically the core D3 layouts don't actually render anything. They are essentially mathematics functions which can take in our data and calculate all the required information to render something on the screen, but they don't actually render anything. We then use the output of this is very similar to in your latest homework, in I think homework 3, we use the path line generator and the area generator functions. So layouts are similar generator functions where they given a data, we get generator functions which we can then use in our enter, exit, or join syntax to generate different elements. And so not surprisingly, a lot of these elements are either path elements where the generator function set the D attribute. So we'll start with like a very basic chart, like a pie chart. Like if you are not familiar, this is what a pie chart is. It's basically a circle where different arcs of the circle encode different data, different parts of our data. Well, pie charts obviously are not ideal, and I'm sure Alex must have covered pie charts at some point. Oh, he will. You're in for like a big lecture on pie charts. But yeah, so pie charts are usually used to show part of a whole relationship, or let's say things add up to 100, like what percentage each data point shows. So to actually draw a pie chart, of course, you can always use the base D3 syntax, draw, and try to draw each line by yourself, but that is very tedious. You'll have to calculate all the different angles, you'll have to calculate the percentages, and that might take up a lot of time. So what D3 gives us is a pie function. And what D3 pie function does is it takes in our data and calculates for each data point. It calculates what percentage of the final pie chart, or what percentage of the final pie that data should cover. So for example, we can look at, so for example, let's look at a simple data here. So we have an array where each element of the array is an operating system for our phone, like Android, iOS, Windows, and like the classic BlackBerry, and then others. So what we see here is operating system and the share of that operating system in terms of like the phones used. Now we can pass this data to our pie function, or the pie function provided by the D3, and calculate a pie chart out of it. So the way we do this is using the d3.py function, which takes in our data and then gives out a new data structure, which has things like the original data, the index, but it also has things like the start angle, the end angle, and the padding angle of our pie chart. So let's just do this. Let's just look at the data. So here we initialize our pie generator function. In the next step, we specify what part of our data is actually what part of our data actually denotes the percentage or the or we want to encode in our pie chart, which is the share. So this is a property we actually want to encode in our pie chart. Now we can pass our data here to the pie function, and as an output we get the pie. So if we try to log this data, we see we have pie data, and if we open the new generated data structure, we can see it has the original data, which is Android with the share of 82%, but it also has things like end angle, pad, start angle. And now that we have all these angles, you would assume that we can now we can start using D3 to actually draw this. But again, still using these angles and then to draw different segments of the circle, that is still a tedious process. And in this case, now D3 also gives us an extra generator function called an arc. An arc is a generator function which can take in the output of the pie function and then actually create paths for us, which we just have to render on the screen. So for example, here we initialize our arc generator function. We specify what the radius of the final pie chart should be. We specify the inner radius to 0. And we'll take a look at this again, like why inner radius is important. And now if we look at our pie chart, now if we look at the data here, so the first arc, we can see this is actually a path, or like this is actually the D attribute of a path. So essentially what the arc function has done, it has generated different paths, which if we render on screen, we end up with a pie chart. And to render our pie chart, we follow the classic D3 syntax where we select all the group elements, bind them to the pie data, which was generated by the arc function. And then we enter and yep. Mhm. So pie data is the second data transform. So first we started with data. This data was then passed to the pie function here. This was passed to the pie function, and we ended up with pie data. And now we will, sorry. Mm-hmm. Yep. So the value function, essentially what we are telling the pie function is that to determine the value, like so we are basically saying in our given data we have, if we look at our data, we have two attributes, right? The OS and the share. So the value function basically tells D3 how to figure out which of these two properties to actually map. So here we are saying that to actually calculate the angle, use the share property rather than the OS property. Does that make sense? Yep. Yeah. So well, the value function tells which part of the data is to be used while calculating angles. Yep. So it's essentially like a map. Yeah. Okay. So yeah. So now again we start with. So now we have our data discussion. Okay. So yeah. So we start with our D3 syntax where we select all the group elements if they're existing or not, bind them to our pie data which we calculated, then we enter and append the groups. Next, now that we have groups, inside each group we append a path element, and then for the D attribute we specify our arc function which we initialized earlier. And essentially, so this syntax looks so this syntax essentially, when we say this arc function, this is essentially the same as doing something like this. Oops, yeah. This is essentially doing something like this, right? We basically, what D3 will do is for each element of pi data, it will pass the element to the arc function, and then the arc function will actually generate the SVG path which was required. If you look at the output, we have the same output. And the shorthand for doing this is just say arc, just pass it the arc function, and D3 will pass the D attribute to it automatically. Then in the next step, we can actually also append, once we have the shape, we can append the text, which is bound to the d.data.os here. So this property to get the name of the operating system, we move the text around so that it fits nicely in between the pie charts. And this is all things that you do apart from the pi and the arc functions, right? So these are just regular D3 things. So now we went over this radius, right? So if we change the value of the radius here, so let's find, yeah. Okay, so the radius here, we are basically calculating using width, height. So let's comment this and just hard code the radius. let's say radius equals 200, we can see that the, yeah, okay, I mean, I think it's 200. And now we can also change the inner radius. So we set the outer radius. If we change the inner radius, so let's say like something like 40, we end up with a donut chart. So essentially, like the inner radius and outer radius together. So the arc function here cannot just be used for pie charts, but also to generate donut charts with like a hole in between. And we'll see there are good cases. There are places where we want to use this donut chart when we, let's say, want to encode some extra information in this empty area here. And that we will actually cover in our next hierarchy layouts section. But before we do that, like, we have any questions on pie chart or this entire layout, the layout functions in D3? Yep. Yep. No, it's like, no, so the actual value here is empty in our data. That's why it's, I'm sure if we give this a label of test, it would show up as test. Yeah. Yeah, but again, like, so now this is unreadable, right? So you would have to then essentially in this, like where we actually add the text and give it a transform, you would have to do some fancy things to make sure it properly, like maybe, move the test outside and draw an arrow, and then, but that's extra stuff. And like, the D3 functions don't really do it for you. And of course, you could use the, since you're using arc, you could use the past attributes like radius and stuff to know how much to offset. But yeah, so I think like for just demo purposes, we kept this empty, and that was pretty much it. Yep. Yes, please. We can test that. Let's do this 0. And it's not a problem because it basically adds up. Basically, it converts everything to percentages, right? So it doesn't really have to be 100 on its own. I mean, our data here already was percentages, so that's slightly, yeah.
And this is like, I think you forgot the
At what point? Okay, yeah, yes. Yes, it's JavaScript, it's optional. I'll let this go back to, yeah, okay, so bad choice of radius because we just do 800 minus 400 by 2, so it was 200 already. Yeah. Okay, so should we move on to, yeah, please. Yep. No, we specify it here in the value function, right? Here we tell pi what to use. Yep. Yep. Okay, so we will now move on to next section, which is the hierarchy layouts. So hierarchy layouts basically denote a relationship between data where we have like the larger subset of data and then smaller subset which belongs or in some ways connected to another subset. So this can be something as simple as a regular tree, like something like a binary tree or a regular tree, something more complex such as graph where there are like many to many relations. Or here, like the first example we have is a chord layout. So if you're not familiar with what a chord layout is essentially this is called a chord diagram, which is basically a donut chart, but we connect part of the different areas to other parts to show certain relationships between them. And like this is this is like used for visualizing, let's say, a matrix which shows how different nodes are connected. So for example, here, let's say we have 4 nodes, A, B, C. So the rows and the columns are the nodes A, B, C, and the matrix and each matrix cell holds the value. Let's like how like A is connected to B, or basically the relation between A and B, how strong is it? And this can, you can think of this is usually something like this is also denoted or also encoded by using something like a heat map, which, well, like a heat map usually has like percentages, but another way to do this is a chord layout or a chord diagram. So let's take a look at how we generate this chord diagram. So you would assume like easy if we remove this. So chord diagram is essentially composed of two parts: the circumference, which is essentially a donut chart, which we saw earlier when you set inner radius to greater than 0, and then the ribbons which connect different elements. And we can see, for example, so this orange ribbon connects our orange area to the brown area. This basically connects the brown area to itself, which is usually the diagonal of the matrix, because these are the self connections. And so we have essentially two parts here: the outer donut diagram and the inner ribbons. And D3 gives us functions to calculate and draw all of this. So let's start by taking a look at. So we load our data here. We select our SVG. We set our set our static variables like the outer radius, the inner radius, etc. So here we kind of calculate the inner radius using the outer radius. We set up our color scales to map the 4 nodes to 4 color. This is hard coded in now. Outer radius is basically just minimum of width or height, and then we divide it by 2. So the width or height of our SVG. So let's, yeah. Just to have some space so that it doesn't like connect to the borders of the SVG, because then you can't really read the labels. It's, yeah, you could think of this as like adding some padding. Yep. Okay, cool. So now we set up our color scale to map our 4 nodes. So in this case, we are just hard coding using d3.range4 to our 4 different colors. Then we use the chord generator function, and the chord generator function essentially, now chord generator function is another counterpart of the pi function, where pi function just calculated the areas. The chord generator function will calculate the areas of the donut chart as well as the ribbons, and we'll see how it does that. So now that we initialized our chord generator, we say add a pad angle of 0.05. So pad angle is essentially the angle, this padding angle between our different slices. So we can keep it to 0 and they will all get connected. So we essentially start with, yeah, we basically create our chord generator function, initialize it. Next, we initialize our arc function to actually convert this chord data into our donut slices. This is the same exact thing as pie chart. We specify the inner and the outer radius for our arc generator. And then finally, we generate the third component of our chart, which is the ribbons. So we initialize the ribbon function and we basically tell it what the inner radius is. And we do this because the ribbons actually connect to the inner circumference of the donut. And if we will try what happens if these two things don't match. So now if we log this, let's clear our console and just log this. Yeah. So if we look at our chord matrix, so when we pass our matrix or our data to the chord generator function, we essentially end up with a data structure which has a source and a target. So source in this case has values like the start angle, the end angle, and this is essentially, then the source is essentially the part of the donut area where the ribbon begins, and the target is the part of the donut where the ribbon ends. And we can use this to render the donuts as well as the ribbons now. And so we start with so we append a group element. We transform the group element to center of our SVG, like to center of our SVG, so our chart appears kind of in the middle. And then we use the datum to kind of bind our data structure or bind our chord data to the group element. And you really have we used datum before in this class? Yeah. So yeah, essentially, so what datum will do is it's similar to our data binding. Instead of binding like an array of data to multiple elements where we need to join or enter exit them, datum essentially says we added this group element, bind it to this data. And we do that for a simple purpose of when we add things to this group now, we can essentially use anonymous functions like this to kind of derive the data directly instead of using it from outside. So yeah, so we can just see it directly here. So we have this new group element we added. And if we just take a quick look at the HTML for this, so we have this SVG, and this was the group element we added. Like all our diagram is inside this one group element. And to this, we use the datum to kind of associate our data here, this data structure. So now what we'll do in the next step is we will add groups to this. So these groups are essentially our the donuts, so part of the donuts. So we select all the groups, we map these groups to the dot groups property from our chords, and then we append the group element to it. Now in the next step, for each group we start appending our path, and then the D element of the or the attribute of the path, the way the path is drawn is using the arc function, and D3 kind of then figures out that the out for each part of the each node or the each point in our data set, the area, the donut chart is basically passed to the arc, and then it's very similar to the pie chart example. It draws the arc, and if we let's say okay, let's go here and set this to yeah, let's set this fill to none. Yeah. So essentially, if we have this, right. Yeah. So essentially, basically apart, so you can also ignore these things like the strokes. So essentially, the first part, the arc function essentially just draw this circumference, and if we put this back in, and now and the next step, so this till this point we basically just draw the donut chart, which was the same as this example. So the code basically we rendered this with just some padding. Now for the next part where we have to actually draw the ribbons, we again go to our group element, add a new group, call it ribbons, then we select all the paths in this group, and the data we append is the chords. Instead of chords.group, now we just append the base chords data. And for each chord we append a path, and now the generator or the area generator for the generator for this path is now the ribbon function, which we initialized here using just the inner radius. And it figures out now using this source and target how to connect these two elements, and how to connect the different elements and how to draw the relations between them. And till this point now, so we append the path, we pass the attribute as ribbon, we style it using our color scale which we generated. The stroke is essentially the color, but a darker version of the color just for some aesthetics. So we're kind of using the color scale and then using some D3 helper functions like d3.rgb to kind of derive a new color out of it. And things like this are like really small helper things in D3 which help you like create really reusable visualizations without actually writing a ton of code. And in the next part now, so these two sections just generate our donut chart and the ribbons to create a chord diagram. And this rest of this code is essentially to basically draw our ticks. So we start by going onto our group, selecting a group tick. The data is essentially we pass the data to a group ticks function which we declared here, which essentially takes the start angle, the end angle, and uses the range function to kind of calculate 0 to pi and things like this. So this is like, you can take a look at this code later. This is not super complex. It just takes the area of the donut and divides it into equal parts to draw our ticks. And the actual tick drawing is essentially just adding a text, adding some transforms so that it looks good. And then a format function which uses d3.format prefix to kind of truncate the result and instead of showing 0.00 things like that. And so a really good example of this chord diagram is, let's see this, yeah. Copy link. So this is a version of a custom chord diagram where there is there is some customized chord diagram code here. This doesn't use the D3 chord function directly. It kind of uses the results to add things to it. So here we can see the difference is in the center of the chord. Instead of the ribbons connecting to another node directly, the ribbons connect to a list of our nodes in the center, and the chords themselves are essentially the location. So this is of course the data set is the Lord of the Rings data set where this is for the movie where it calculates the number of words spoken by each character and connects it to the location they spoke it in. So for example, Gandalf has spoken very few words in Mordor compared to Shire or Moria. And then we can see that, let's say, yeah, in Lothlorien, the Gandalf wasn't there, like spoilers, I guess. But yes, so this is a pretty cool chart, and this was created by Nadi Bremer. She's like a freelance data visualization person, and she does really, if you look at her website, it's here, visualcinnamon.com. It does a lot of really cool visualization, like very artistic visualization for like movie and the games data set. They're really good to look at, and on this link you will find all the code that is required. So of course, like this doesn't use the base D3 chords directly. It has some customization. It has really cool interactions which you can take a look at when thinking about your projects. But yeah, so this is an example of how you would use a chord layout. So next we'll move to tree layout. So before that, any questions regarding this? Okay, no. Okay, so tree layouts. So I'm sure like all of you know what a tree is, but let's just take a look at tree. So this is a tree. So tree basically just denotes a parent-child relationship, and of course this has two nodes. It can have multiple nodes. So it's basically like a one-directional graph, like one-directionally cyclic graph. So now to render a tree with D3, we have a lot of this helper functions again. So, and of course, like tree layout is commonly, it's like it's one of the most used visualization for hierarchical data. And we'll take a look at other visualizations like graph layout, but for tree layout, the basic function that we will use from D3 is the tree function. The tree function takes in our data and basically gives us the information necessary to render the parent-child relation between our data set. And to do this, we use another helper function called hierarchy. So D3 hierarchy is another helper function which can take in the tree data structure and calculate the necessary relations between them to basically make our life easier while rendering it. So let's look at our data here. So we have a JSON with the first element as name. This is our root, and it has a children property which is an array of other elements. First child is again just an object with the name Cain, which has no children. So this is the leaf. Then second child is Seth with two children, Enos and Noam, which are leaves in themselves. So you get an idea of how the data structure which D3 accept looks like. It's essentially just one object with children property, which may or may not be empty. Now our data, and then this data is just passed to hierarchy, like the hierarchy function, which calculates some D3 specific things such as positions for it. And we'll take a look at the details. But usually our data sets are not in this format. And you must remember from the homework we did, where we had this flat parent-child relationship where we had to write this function to kind of add the parent and child relation, calculate the positions and levels. Essentially we get to skip all that, and the way we skip this is D3 provides us. So this is very similar to the homework, right? We have each element is a node, and then we have a parent for it. That's it. And we wrote some code to kind of create this data structure of adding parent-child relationship using the node.js and a tree.js in our homework. But there is an easier way to do that. There is a Stratify function which can take in this flat data structure and generate everything. So basically, everything on the second homework you did for calculation is just one line of code now. You just use the Stratify function here. And the way you do it is you start the Stratify function, you tell the Stratify function how to figure out ID for each node, in this case is just d.name. And then you tell it how to figure out parent ID for each node, which is d.parent. And doing this will essentially create a data structure like this, where we have the outer node and then it has children. So the outer node here is Eve. It has no parent, and it has a children array where where the childs are Cain, Seth, Abel, etc. And of course, then we have here depth and height, which you manually wrote recursive functions for assign level and assign position. Stratify adds those automatic. So hierarchy adds those automatically for you. So essentially, we are doing two steps here. We are taking our flat CSV data structure, giving it to Stratify to get an hierarchical data structure, which we then give to the hierarchy, and hierarchy adds the position and level data, and that essentially we end up with like a good data structure to pass to it, to our tree function, which will actually give us XY coordinates. So at this point, let's look at what the actual data will have. So of course, the each node which we get out from the hierarchy function will have a data object, data property, which is essentially the associated data. It will have a depth and a height, which is basically the level and position from our homework. Then it has a parent, a way to find out what the parent is or just the parent node. It has an array of the children, and then the value. So the value is essentially an aggregate of, basically it uses the descendants to basically count some aggregates of like the total number of descendants it has. So, and this probably is not as useful as the rest of it. And then each node object also has some functions called ancestors and descendants. And what these functions give us is essentially all the parents all the way to the root. So we can at any point call the ancestor functions, and it essentially gives us a path to the root. And descendants essentially gives us an array of paths to all the leaves or all the subpaths. So now that we have our root node, which is this node is the root node, we can just pass this to the tree function. And what it gives us, what this tree function does is it travels through this entire root or the tree and adds the X and Y coordinates. And all we are left with essentially is now taking this X and Y coordinates, just rendering them using our D3 syntax. So let's now look at the code for completely rendering a tree. And if we, let's look at our output first. So we will render a tree like this: top level, level 2B, level 2A, and we have some fancy interactions here where we click on it and it actually opens a subtree. So level 2A actually has son of A and daughter of A, and of course this is all animated. So now let's take a look at how we can render this completely interactive animated tree. It's a lot of code, but we'll just walk through it. And please feel free to stop me at any point, because this code is slightly, it moves up and down a bit. So this is our base tree structure. In this here, for this example, we are assuming that we already have like a nested data structure. So we don't have to call Stratify here. We just have name, children, and a data structure like this. So top level, which has two children, like level 2B and level 2A, and level 2A has two more children, son of A and daughter of A. So this is our data structure. We set up our SVG dimensions, and then we basically select our body, add the SVG, position it correctly using margins and stuff. And now we actually start generating our tree. So first we initialize our tree function and give it a size, which is of size of the SVG we want it to be limited to. So this basically gives us the outer widths of the tree, so from root to the last leaf. Then we create our hierarchy function and pass it the tree data which we had earlier. So essentially this data. And then we basically tell the hierarchy function how to access the children, because again, children is not like this magic property. You can call it anything. You just have to specify it here what the array of children is called. Then we get this root data structure, and we can just console log this root data structure to see what it looks like. Okay, so yeah. So we have this root data structure which has the data, it has two children. And what we'll do in this case is, now that we have this root data structure, we will just add a x0 and a y0 to it. So this is like the initial position of the root, or initial position of where we want the root to be. And you can see there is x0 and y0, which is the initial position, which is same as the final position, because root really doesn't move, right? Root is always at the same point. And then what we do is, for each child of the root, we collapse the nodes. And so just for now, collapse function essentially allows us to hide the nodes when we click on them, and we'll take a look at how it works later. But let's assume for now that it works. And what it does is, for each child, it recursively goes in and hides everything. And when we are done, we just call the update function on the root, and update function is what the update function is the one that actually renders our tree. So now this is where we actually start drawing everything. So now we take our root, which we got from a hierarchy, and pass it to the tree generator function. So basically we take this and pass it here. Where, yeah, okay. So, and then the output we get is the tree data. So let's take a look at what tree data looks like. So just log tree data. And we can see the tree data is like, basically it's essentially a very similar data structure, but if you look at all the different children it has, yeah, you can see like it has different x zeros and y positions now added to it, this was essentially added by the tree map function, because tree map knows what the height and the width of the total tree should be, so it adds the proper x and y positions here. Then we can get the, so let's just comment this, so clear the console. So now we need to get so this tree data is basically essentially a nested data structure, right? And for D3 to render each node and the links between them, we need two iterable data structure or two lists. So the way we get this list is, for the tree data, we get all the descendants out of it. So tree data dot descendants will basically go from root till all the leaves and give us a list of all the nodes. And the links here, in this case, the links are essentially the descendants minus one. So we just skip the root because nothing connects to root. And so that's why we do tree data dot descendant and slice. So slice will return us so slice one essentially says, take everything in the list starting from the first element till the end, or starting from index 1 till the end. So we skip index 0. Then we basically, so this nodes.for each, this essentially goes in and updates the d.y property, multiplies it by 180 to kind of basically make sure the y position is properly shown in our SVG. So this is like normalization, so that our widths, so our heights are assigned correctly. Then we start actually rendering the node. So we select all the group elements. This is like another way to select. We can select all the group elements with the dot node class on them. And so this is like a slightly different way of combining both. We could also, I think we could just select all elements with the node class on them, but this basically says it should be a group and it should have a node class. And then we bind it to our nodes data structure, which we derived from Descendants. And actually, before we can just log how the nodes and links look like. Yep. So you can see like the nodes are essentially the list of our 3 nodes from our data structure. So the dot descendants kind of flattened all the nodes for us in a list. And edges is essentially, it just ignores the first element because we just took a dot slice. Okay, so yeah. So now that we have these two arrays, we use the D3 syntax to bind the data, and then we specify the ID function. So what ID function does is it basically tells D3 how to keep a track of this particular object when the data updates. And the reason we do that is because when we collapse and bring back the nodes, we want the existing elements which are not collapsed to stay there and not re-render. And this is a slightly weird syntax where we are saying use the d.id, but if it doesn't exist, assign the d.id and just assign the d.id. Wait, where is the I function here? This is the index, yeah. So use the d.id or just increment the index and assign the ID. So basically on the first pass, it will assign the ID if it's not there, and in the second pass, it will just keep using it. This is, yeah. So we can see that here, this elements themselves, like the IDs are assigned like basically at this point. And because JavaScript is slightly funny, the console log was here, but IDs were still assigned because JavaScript does everything by reference. So, but yeah, so essentially we could have just manually wrote a for each loop and added the IDs on our own. That is perfectly acceptable. The only requirement is that ID should be unique and repeatable for each node. If, for example, let's say during the second run, if we somehow change the IDs, the nodes will move from some places. So, okay, now that we associated our nodes with the groups, we actually append the groups. So we go to our enter selection, we append the groups for newly entered node, we give them a class of node because that's the criteria we use for selection, and then we transform them. And here we can see that we are transforming them to y0 and x0 of our source. And the reason we are doing this is because we want to animate our nodes when they're added. So what we are saying is add a node in the same position as its parent, and then we will animate it to its correct position. So first we just add it to the position of its parent or the source, and then we stop there. Then we add a click event listener. We'll see this click event listener is what handles the collapsing, and we'll see how collapse and this event work later. Then for each newly added node group, we actually add the node circle. We set its radius to be really small, like almost 0, so that the node is rendered on top of the parent, but it's just not visible, because we will move it to its correct position and then animate it to be visible. And then we fill it. So for filling it, we have a criteria where if the children exist for the node, color it in light steel blue color, it's just color it in white color. And now we actually add the labels, and the code for the labels is pretty straightforward. We add a text, we offset it somewhat depending on whether the node has children or not. The label is slightly shown in a different place, so these are just different places for the label. And then finally the actual value of the label is d.data.name. So if we open this, so we go to this node, data, and the name. So this is where the label comes from. Next, we create our update selection, which is essentially enter selection, which is merged with our original node selection. This is the D3 syntax. And then on the update selection, now we want to animate everything together. So what we did here was we split our work. When rendering a new node, which wasn't present earlier, render it on top of parent and make sure it's not visible. And then when we update it in the update loop, then animate it to its correct position. And during the animation, we use the transition function, set the duration of our animation. So here we set it up to be, let's see what the value was, for 750 milliseconds. Where were we? Yeah. And then we transform it to its correct position. So this transition and duration are applied to our transform. So now when we give this, so our original transform was basically on source x and y coordinate, and now we give it the actual x and y coordinate from the D and or the node itself. So we are now moving from parent to from the parent's position to its own position. And then of course, like when we are changing this, we are using the D3 transitions, basically then update the transform value incremental instead of in one go. Now this was for the outer group, right? So the node update was applied to group. Now inside each group, we select a circle, and then we also update it, and then we now set the radius, which we earlier set here to be really small, like 10 to the power minus 6, to be actual radius of 10. The colors are still the same, and we add a cursor pointer attribute so that the nodes themselves become clickable. So cursor pointer basically changes the shape of the cursor, and you can like use this on anything. So we can see the cursor changes to be the small hand sign, which is like a standard to show that something is clickable. So yeah, okay, so let's come back to this. So yeah, so we updated the selection. So now till this point, what has happened is our newly added nodes are rendered. Then in the update cycle, we have moved the nodes to correct position. The only thing that is left is if there are any nodes to be removed, to handle those. And again, we start by the same thing. We select all the elements using the dot, like node.exit basically selects all the nodes that are not good. So select all the elements on the screen which don't have nodes anymore, where the data structure is updated. Let's say when we collapse, the children are not there anymore. So we have to handle the like the SVG elements for those children. And then of course we want to transition them when we remove it. And the transition is essentially we move the children from their position to the parent position and remove them. That's it. So we get this nice animation of, so let's look at this. So first this is rendered. Then when we expand this during the update, we see that the elements move. So you can see like I don't know if it appears on this, but yeah, like very slightly you can see the elements appear on the root and then move to correct position, and same goes here. And when you actually move them back, you can see the elements move toward the parent and disappear. and that's what our exit does. Where were we? Yes. So yeah, so this removes them, and then another. Now we want to. So this basically this part of our animation basically just handled the position of the node. Like when you collapse, it goes back. We actually want to handle the animation where the size of the node also reduces. So we also update the radius property to be 10 raised to minus 6. And the text, we also reduce the size of the text. So when we actually see something collapse, you can see that they are shrinking as they go towards the parent and then disappear. So this was just the code to render and animate our nodes. This actually doesn't render the edges between them. So now let's render the edges or links. So in this case, we again start by selecting all the paths with the class of link and append them to our links array which we derived. And the ID for the links is just d.id. And this works because when we were doing nodes, it kind of added the IDs already. And when we do the enter, so now we can do link.enter. And so here we are using a slightly different syntax called insert path in a group. This syntax, yeah, so this is just an this you can replace this by select a group and append. So essentially this could be something like dot select group and dot append. But to do this, so do this in one step, you can use the dot insert syntax. Like if you are comfortable using this, you can. Otherwise, just append works fine. Then we give this newly added path a class of link, and then we set the D attribute. So now when we are doing the enter selection for the link, or when we are rendering a new link which wasn't there earlier, we just say the link goes from source to, so we just say the link is calculated using this diagonal function, where the source or the source and the target is the same, because we are just passing the same x and y for both source and the target. And let's take a quick look at diagonal function. So diagonal function basically takes a source and a destination and creates this path out of it using Bezier curves to create essentially this curved path. We can replace this with a straight line if you want, it doesn't matter. So when we pass the same element for source and destination, it will essentially create a path which goes from itself to itself. And this is because when we are first adding it, we want it to be on the parent itself. Then we merge our links, newly added links with the existing links, and then we transition them to their correct position. So we transition them to their correct path using the, and in during our transition, during our update, we can see we go from D to D dot parent. So now we can actually connect. So now this is how we draw the link from child to parent and animate it. And of course, the last thing we do is we remove the links we want when we collapse using transition, and then essentially again set the part to from itself to itself. And then we remove it. If we don't do the dot remove, what will happen is the elements will shrink and it will just remain there shrinked. It will never be removed from the HTML. And that becomes problematic when you have too many elements, your browser will slow down. So when you're exiting, it's almost always a good idea to do a remove. It actually removes the DOM elements. And the last step in this is, now when we finally update everything and calculate new positions for the node, we essentially go through each node and store the x0 and y0 to have the old positions for the node. And we'll see how and these old positions are used essentially when we want to calculate like the dot x0, when we do source dot x0 and y0 here. Let me see. Yeah, here. So essentially that's the reason we save this x0 and y0 positions for all the nodes. And now let's take a look at our collapse. Like how does collapse actually work? So we have two parts for collapsing. One is the actual logic of collapsing things, and one is the actual event handler for collapse. So collapsing is actually pretty straightforward. So the one way to do it is like to keep a track of all the collapse nodes and then just not render it. But then that basically says the responsibility is yours. You have to like add a conditional. Another way is something really like something to trig the D3, where the D3 tree expects a children property to kind of render children. So what we do is when we want to collapse the children, we check if it has children. We just rename children to underscore children, and then the original dot children is null. That way D3 thinks this node doesn't have any children. And that's essentially how we have collapsed without adding any real like logic to the rendering part. So our rendering part doesn't change at all. And this collapse is actually triggered using our click function, click handler function, where we check, where on click we check if the children exist. We essentially like you call the collapse function, or like basically do the same logic as in collapse, and then we call the update. And the collapse function we declared earlier is used here. Where did it go? Is used here in our for statement to initially collapse everything we want. So yeah, so this is slightly big part of the code. Like you will have to spend some time going through this, but this is like one of the first codes that really covers complex transitions and complex paths. So like we can go through some questions for this code if you have. Yep. Mhm. Yes. No. So for example, so in SVG path specification, so for example, this M says move to this Y and X coordinate. This C essentially says draw a Bezier curve from source to destination with this third point in between. And this is like the SVG implementation of Bezier curve. So this is basically what you get in a browser. Yeah. Yes, exactly. Yeah. So this should like technically this should be let path. Yeah. Yeah, exactly. So SVG notation, when you say C and give it 3 point, it calculates a Bezier curve with the point. And of course, you could like the syntax supports like adding points, and there are different type of curves. You don't just have to use Bezier. Like if you look at the specification, you can draw different type of curves. But in the end, basically what we're saying is like this function, you can just write your own logic and create a complex wiggly path if you really wanted. It doesn't matter. Yep. Yes, you can. Yeah. I mean, this is essentially like a mind map, right? It's all about once you get your data using the hierarchy and stratify functions to kind of get the actual layout and then give it to tree function, get your XY, and then render. Yep. Yes. That's a good question. Let's see what happens if we use 0. Let's see. Yeah, let's while entering, let's just use 0 and see if we get any errors. It shouldn't. No, you could use 0 also. Yeah, you could use 0. Yeah. Any more questions? Okay. Yes. Mm-hmm. Okay, line 163. Yes. Yeah. So basically, what we are saying is insert a path into a group element. So this is essentially normally what we would do at this point is for each entering object, we would select a group which exists in the link object when we select all, and then append. So then append a path to it. Yeah. So now we are basically replacing that with one single step called insert, which says insert a path into an existing group element here. And it just like just this is just one of those D3 syntaxes. Like you don't have to use insert. Like actually, I never use insert. I always use append. Yes. So yeah, attribute is the generic way of specifying any attribute on any SVG or HTML element, and dot class is specifically for. So like the reason you would use dot class versus attribute is, let's say your element already has a class and you need to add one more to it. If you just use class, it will add it or remove it. If you use attribute and don't mention the original class here, it will just replace the original class. Yep. Okay. Any more questions? Okay, cool. We will move on to our next layout, which is a tree map. So now we looked at our tree layout, which draws this, which draws a tree, like a parent-child relationship tree. We will now draw a tree map, which is essentially this this diagram where we use areas to kind of show the hierarchy. And so essentially in a tree map, everything you see on the screen is the leaf, and the colors kind of denote the way they belong to each other. So here, for example, we can see, and the data set we are rendering here is actually our, we are just rendering the D3 code base. So what we are rendering is how the D3 code on GitHub is organized into different files and folders. So, or different modules. So for example, here is our, so this, from, if you look at the names like Albers and Mercator, you will realize this is the D3 geo module. And if you can, is the tooltip visible? Yeah. So basically in the D3 geo, in the projections folder, there is a Mercator JS file, and this visualization kind of renders this file browser into this tree map. And we can see that, so here everything here is part of the projections folder, and you can see that this is not a great example. Yeah, so this one, so this everything here is part of the, let's see, the D3 interpolate folder, versus everything here is part of the D3 array folder. So these are all our array related functions. And this is essentially like, if we used a tree diagram to draw this, we would have a node for D3 array, a node for D3, and then a relationship between them, and it would get really big. What this does is this essentially renders only the leaves, and kind of the nodes are shown by the area and the proximity and the color. So to just take a brief look at the code, like, we will not really spend a lot of time on tree map. Like, I'll run through the code quickly. This doesn't really have any animations and stuff, so the code's quite easy. So we essentially, the data set is like this, right? So we have size, or size here, it's, I think, the number of lines in the file, and the path is the actual file. And then we essentially use the path to kind of split. So for example, for array.js, ascending.js, bisect.js, the parent is the D3 array, and the parent for D3 array is D3. So D3 is kind of the root node here. And instead of using the tree function, we will still use our hierarchy and we will still use our stratify function. But instead of using tree function to calculate the layout, like tree function adds x and y, we use the tree map function, which adds x0, y0, x1, and y1, which are the corners of the rectangle, or like the top left and the bottom right edge of the rectangle. And we just render this to the screen. So let's just start with the code. We select our SVG, give it a width, and we get the width and height of the SVG. We create a color scale, just pick one color scale from the D3 color scales. And we create a format function to kind of format our sizes here. So number of lines, like we add the comma in between them. Oops. Yeah, we add the comma in between them. So this is our formatting. Yeah. Then we initialize our tree map. We give it a size, like the total size of the tree map. Round property, we set the round property to true. So round property, essentially, round property in a tree map basically makes sure that the areas of the, like the positions of the rectangle are rounded to the nearest pixel values. So it's not something, they're not like half a pixel or something. On this scale, like if I set this to false, you won't really notice anything because the visualization is so big. Then we add a padding. Padding essentially is the space between the different areas of the tree map. And of course, we will, like in the next lecture, Alex will go deeper into what this data structure actually encode and what are the best practices, how to use them. Like the focus of today's lecture is on how to render, once you choose a tree map, how to actually render it. So then we have this like a variable which stores the versions. So this is like a helper function to actually get the file names from the GitHub. And now we actually start by loading our D3 or loading our data set. So the way we load our data set is using the d3.csv. This is very unfortunate. So this is the name of the file, and this is the CSV function. Yes. And so we are using, so someone on Slack asked, in the homeworks channel asked why we are using update, why we are using await when we use d3.csv or JSON sometimes. So this is another option for using await. So essentially, D3 CSV and D3 JSON are async functions where JavaScript kind of says, I will run this function, but I won't wait for it to complete. I'll just move on. And this is because file loading can be really expensive. One way is to tell JavaScript to just wait for it to complete using the await keyword. Or other word is using this dot then, which basically says when you are done loading this, then run this. And basically the result of this CSV is this data here. And then now we can just use the data. So we start by using the Stratify function. Since our data is not a tree anymore, we first convert it to a tree-like data structure using Stratify, where we say that the ID is the actual path itself of the each node, and the parent ID is essentially take a substring and load the last path. So here, so for example, the ID of the parent is essentially this. So take a subset of the path and load the second to last element. So we use the last index of, and we take a substring from 0 to last index of. And of course, the substring function is not inclusive of the last element. So it goes from 0 to last index of -1. And that's how you get the parent ID. Then we actually pass it the data, and we'll take a look at, so we'll take a look at, yeah, this is the data which we read from the CSV file. And then we do a sum to basically add up all the sizes. So because in this case, like what we want to do is basically, for let's say the total number of lines in the projections is basically the sum of all the lines in the individual files in the folder. So we just add this using d.size because that's what our data is, this size. And then we sort these functions from basically using the height and the value. If we don't sort this, basically this will look slightly uglier, like the rectangles will not be just be arranged haphazardly. And we might take a, if we have time, we can take a look at if you remove the sort function, how it looks. So now that we have this like results of the Stratify, we can now pass this to the tree map function. Earlier we passed it to tree, now we pass it to tree map, and we get a new data structure out of, and this tree map function basically adds information to the root, or adds information to this root element or the root data structure. Let's clear this. Yep. So now let's start adding our actual elements. So we select, in our SVG, we select all the anchor elements, and here instead of adding a group or SVG, we are adding some like an anchor element, and anchor element is used here. This is the anchor element. An anchor element is used in SVGs, is used in HTML or SVGs to kind of show a link. When you click on it, it opens something. So for example, if you click on this, it opens the actual Circle.js from GitHub. So that's the entire point of using an anchor element. So we start by adding an anchor element. The data for this anchor element is basically the leaves of the tree, because we are rendering, the tree map renders the leaves, and it doesn't really render the parents themselves. It renders all the leaves. And we append all the anchor elements. Then we set the target property. This is again like not very important to visualization, but target blank essentially makes sure it opens it in a new tab rather than the same window. And then we actually set the link. And the way we set the link is we just use github.com. Then we append this string using our versions and the name we got from our CSV to kind of generate this string, where we have github.com/ this part comes from our files, like our CSV file. Then this blob is hard coded. This version number comes from this version array which we have here, and then the rest of it again comes from our file. So this is basically a complex string generation. Like you don't really have to worry about it a lot. It's just connecting different parts together. And then we translate it to the correct position. Like we just now translate it to its x0 and y0 position. So this will basically, at this point, we have we have rendered all our anchor elements, and anchor elements are empty. They don't actually have any data. It's just empty rectangles. Then we actually add a SVG rectangle to it, give it an ID, give it a width and a height and a fill. And this fill basically uses the, so the way we calculate fill is we have the color scale which we defined here, the scale ordinal, and we kind of use the we use the hierarchy. So basically the color scale is derived from the parent of the leaf. So here we have, for example, the closer, for example, the closer the two files are to each other in the hierarchy, the more similar color they will have. So for example, here, like they have the exact same colors, but for example, if you go like far away in the folder structure, you see the colors start really differing. So essentially we use this ancestor, we use the ancestors function and the length of the ancestors to kind of determine how far, like what part of the color skill they should belong to. And again, this is completely up to you, right? You can basically, if you know the number of like categories you have, you could essentially just replace this with some other scale function. Then we append a clip path. Again, this is a different type of SVG element, which essentially says that the click should work on all parts of the rectangle rather than just the text. So it basically allows us to click anywhere and the anchor element works there. So like again, clip path is probably not something you would end up using a lot, but it's there. And then we actually append the label. So we append the text. Then again, we add a clip path so that the click works on the text as well. And then to the text itself, we add two small tspan elements. So first one is here, the second one is here, because we want in the same text, we want the two different part of the text, which is the name and the number of lines, to be formatted slightly differently. So you can see the first tspan, we actually add the text, which is basically the substring, and the last index of this basically is the file name. It will exactly take the file name, remove the .js extension, and just render the file name here. And the second tspan is just the value, which is the size. And the last thing we do is we add the title. So title basically adds a tooltip. So when we hover our mouse here, we see this small tooltip with the full path, with the complete file path, which folder it belongs to, and everything. So like that, and that's a problem with tree map, right? You don't really immediately looking at this, unless you add something interactive, you don't really know that all of these elements belong to the projection folder. So that's one of the drawbacks of the tree map. And you could do that where you add some interaction where on clicking, where initially it will just show one big rectangle as projection, and when you click on it, it shows the smaller rectangles for each file. So you could always add that interaction, and then your tree map becomes capable of rendering more and more data. So okay, this was like a quick rundown of the tree map. And okay, any more questions? Because I don't know if we'll be able to complete force layout today. Yes. We can run through it. But okay, so I won't take questions. I'll just go to the next part, which is network layouts. So with the main part we want to complete here is the graph, visualizing a graph. So this is essentially what our graph looks like. We have nodes and the edges connecting the nodes, and the data structure for that, the data structure which D3 expects is something like this: an object with a nodes array and a links array. And of course, like this, you can change I think you can change the name of this and specify it individually. But essentially, the nodes themselves have ID, a group, and whatever data you want. And links always has a source, a target, and the weight for the individual link. So let's say two elements are connected more strongly, their edge might have a higher weight. So for this example, we will use the Miserables dataset, which basically has character co-occurrences, like how frequently the two characters appear. And before we start that, like there are multiple different ways to show or render a graph. There are different graph layouts. The one D3 provides is called a force layout. And force layout essentially mimics the graph as if each node, like the nodes themselves are connected, nodes themselves repel each other, and they are connected by a spring which pulls them together. So basically it's kind of it models this like the spring mechanics. It models them in like a spring mechanics way and figures out how the final graph will look like. And the goal of this graph is strongly connected elements should appear together, and less like weakly connected elements should be far apart from each other. So something like this. In here you can see in this animation, like this is how the graph resolves. So similar elements are together, more connected they are, the more together they are, otherwise the far apart they are. And we'll take a look at how D3 does all of this. So the way the D3 uses something called as forces to calculate the relationship between the elements of the graph and how they are connected. And the main function to do that is the force simulation function. And the different type of forces it uses are the links, the charge, and the center. So we'll take a look at this individually. So, and we'll take a look at it as when we remove one of these, what happens. So link is the force which determines if the two elements are connected, how they should attract to each other. So if we remove the link, so if there are no connections between the element, the nodes will simply repel each other and just move away from each other. Next we'll look at what happens when we remove the charge. And charge essentially is relation between any two nodes. They may or may not be connected, it doesn't matter, but basically how they repel each other. So here, if we remove the charge, the nodes just don't move from their place because there is nothing to repel them. They just stay on their position. And then the third one is the actual. So third one we'll remove is this center, and center essentially is like gravity, and it basically says if we remove this, our nodes are basically rendered in the top left corner of the SVG rather than the center. So the center of the SVG is usually used as the center of the gravity. So, and these are like the three basic forces we specify, and basically we have to just specify them using inbuilt D3 function. I'll show you quickly how you can actually change their values and adjust them so your graph layout appears better. But some of the other functions we can use are a collide function. Collide function basically says that each node is surrounded by an invisible circle and no other element can be inside this circle. So this makes sure that you never have nodes which overlap each other. So this kind of gives you a way to spread this out. You can see like when it settles down, you have this like equal spacing between everything. And then there are force x and force y, which is like very plainly a force in x direction, or like basically how the entire graph should move in x direction, how the entire graph should move in y direction. And now we'll look at basically quickly, I'll share this link later. This is like a testing ground where you can kind of play around with different values using the sliders and stuff, writing the code. So for example, if you increase the charge, the elements try to appear together. If you basically increase the collide radius, they basically start going further apart from each other. If you give it a force x, it basically moves, they all move towards the center in x direction. If you give it a force y, they all move towards the center in y direction. And then the link itself essentially is how strong the actual connected edges should be. I'll share this later. You can play around with this. And basically this playground is a good example of where you can use the UI to adjust all your values before you write any code. And now let's take a look at how to actually write the code to render this. So we start by selecting our SVG, select our scale, then we set up our force simulation. So the simulation object holds, we initialize it using force simulation, and we add all the forces we want to it. So the link force is essentially saying if the nodes are connected, attract them. The charge force essentially says the nodes should repel each other ideally. And then the center says all the graph should be centered in the center of the SVG. So now that we have this, again, we use the same .then syntax to load our miserables dataset, which is accessible in the graph. We first add our links. We add the individual links first. And for that, we append a group element, give it a class of links. And then the links are going to be represented by straight lines. So we add the line element. We select all the lines. The data that we map to them are, let's just map our console logs or data here. So the data that we map to links is this links array, which we get from our data set. Then for each element, we append a line. We set the stroke width. So the line, so how thick the line should be. And that is dependent on the value attribute in our data. Then we add our nodes layer. We give it a class of nodes, select all the circles. We map it to the graph.nodes property here. We enter append a circle, set the radius, set the fill using our color scale. And then here is something we do here that is completely optional, is we add drag event handlers, which I'll go through like at the last stage where you can drag the elements. But you notice like in both of these codes, we actually didn't specify the position of the nodes or start and end for the line. Essentially, if we run code only till here, everything will appear at one single point on the SVG. And the reason is because we really don't want to specify the positions on our own. We created a simulation object and we want the simulation object to position the nodes. So now what we do is we pass the nodes which we got to our simulation object. We pass it the links using the force link. This is, so basically this is the syntax for passing nodes and the links. We pass it the links from our data set. And then what we say, then we set up a tick event handler. So what we tell simulation is, on every tick or on every iteration you do the physics calculations, update the links and the node, like the x1, y1, x2, y2 position, and the cx and cy position for the nodes during the animation, which essentially gives us, basically when we move things, you can see that things are slightly adjusting. That's when the simulation is kind of running. And if I just rerun this entire code, yeah, you can see when it was calculating from its initial position till it settled down, the basically everything is animated properly. So that's why we actually never, when rendering the force layout, we don't provide xy positions directly. We provide them through this onTick function, and onTick function is essentially run on every iteration of the calculation which the simulation function does. And there are like there are libraries like extensions to D3 which provide different versions of the simulation function, which like may or may not be more efficient. But yeah, like I won't go through those now. Now let's take a look at the last thing we did here. What we did was, on each node, we added a drag event handler, and we specified the start, when we start dragging, when we are dragging, and when we finish our dragging. And these are the three functions. And let's take a quick look at what the individual functions do. So when we start dragging, we want to basically store the current position of the node when we start in like an fx and fy variable. Then when so fx and fy are basically the dragged positions or the temporary position when we are dragging. When we are actually dragging, we replace the x and y, the fx and fy, with the event drag. So event basically has the mouse position when we are dragging, we replace it with that, so that when we are dragging, the node follows our mouse like this. And then we are finished dragging, we basically set the fx and fy to null, because now that is the final position of the node. And essentially what this does is, when we finish dragging, it runs the entire simulation, the force simulation again, to kind of finalize its position. So if we see, like, if we move it, it kind of goes back. General shape of the graph remains the same, but the entire graph is shifted because the physics calculations, they are not really repeatable in that sense. But yeah, so this is like how you render a graph using a force layout. So this is, let's see if this link works. I don't know if this works. So like this link, basically you can go through like individually, like how these functions work and what they do. And this is like a good slideshow of basically having different, like how to test out individually in isolation what different forces in the simulation do. So last thing I want to quickly go over is, for all of this graph stuff, there is a library called Cytoscript Js, which actually has a lot more different layouts other than force layout. It also has a lot of different graph algorithms for like traversing it efficiently, finding paths, etc. And it's a really cool library. It's also a tool of its own, and you can see there are a lot of different layouts already here available to you. You can use directly if you, let's say in your project, want to render a graph. And the code for it is pretty simple, right? You get your Cytoscape object, provide HTML element where you want to render everything, style your nodes, give it the data set, and basically then just name of the layout you want. So this layout is called a Koze Bilkent layout. So it was developed at the Bilkent University in Turkey, and it's basically kind of like a spring layout, but this example isn't animated. But you can see like the library on its own gives you things like zooming in, zooming out, moving, selecting, and all of this without really writing a lot of code. So Cytoscape is like one library you want to look out for if you're using graphs in your projects. But yeah, so there are like other different layouts you can use in D3, and Alex will actually cover a lecture on when to use which layout, what different part of the layouts mean, and how to use them. But yeah.
Thanks, Kieran.
Yeah. Should I stop streaming?
Yeah, just one note. On Tuesday, we'll be doing a theory lecture, but I'll also be going through what to expect of the exam. Thanks, everybody.
Command G doesn't work?
It should first escape.
Okay.